Okay, so let me little bit repeat what was last time, because I fear it was too fast and too much. So we constructed what is called non-standard universe, but let me remind you. So we started from construction universe. So we started from some basic set S, S0. No, for example, the set of real numbers. It's enough for all the mathematics. Then we constructed the sets S1 equal S0 and sets of S0 and so on. Sn plus 1 is Sn union P of Sn, and the S check is union Sn and from 0 to infinity. So just countable union of countable union of sets. It's okay. And as I explained, in this say hierarchy of sets, you can find all the objects of our mathematics and a lot of more, mostly trash. But all our mathematics is here. Now, then to define more things, we use the language L. So this language contains the following symbols. It contains the symbols, logical symbols, there exist, and forgot brackets. I think that's it. It contains also variables. Countable set of variables, and it contains constants. Constants are in one-to-one correspondence with elements of our set S check, so that every set has its own name. So I would distinguish between the sets and their names. Name is just name, and the set is something material. Constants in one-to-one correspondence with elements of S check. So if you have some elements, say A in S check, some either the individual from S0 or any set from other levels, then its name is say A. Like this, boldface A. So we have to distinguish. In the formulas we use these letters as constants, and they are the names of these. So this is our language. And now we use the basic constructions of our language are terms. Terms are either constant or variable or their combination. So say constant C x. So this constant, this variable. Then if mu and nu are terms, then say the pair mu nu and mu on nu are terms. So mu restricted on nu is say if mu is a function is also a set. Yes, then mu restricted on nu is the value of the function at the element nu. Yes, so mu should be some set of pairs, and mu should be some first term of some pair, and then the result will be the second term. If mu is such a set of pairs or such a relation that there is no mu like this, then it is empty set, no result. If it is more than one nu, it is also empty set. So these are terms, and so using these operations, we using these operations with terms, we can compose further and further and make arbitrary long terms. For example, suppose that you have two sets. A and B are elements of S. Check, no, they are sets, so minus S0. They are just sets, they are not individuals. Yeah? Then how can we regard the thing A union B? This is not, what is this? I claim that this is also a term. Yes, so individual set is a term. Yes, no, strictly speaking, we have to write here name of A and name of B. Yes, but what is how can you express this union as a term in this sense? Yeah. Consider this operation of union. Yes. So we take two sets. So let's consider operation. Union of AB. Yeah. No, in our naive sense that union of AB is A union with B. Now consider the following relation. Union A, B, C. So where it is? It is a relation. So it is a subset in, say, Sn times Sn times Sk. Yeah. No, to be clear, let us take, say, m is more than n and k, or more or equal. Let us union ABC is a subset in Sm times Sm times Sm. Yeah. So what is this? We say that A, B, C in union sorry. If C equals A and B. Yes? So we consider triple of sets and say that it is element of our relation un if C is union of A and B. It's okay, so where is this un? So if ABC in Sm, then the triple ABC, so A, B, C is element in Sm plus 4. If you recall, we derived that if you have two elements in Sm, then their ordered pair is in Sm plus 2. Triple is ABC is by definition yes, A, B, and C. So it is iteration of forming a pair. Yeah.
So it's a subset of the union of subset of M, Sm times Sm times Sm times the third line. So for which union actually?
Excuse me?
For which set of union?
Union is C. Yes.
Second upper one. Yes, this one.
So it is A, it is B, it is C. It is A is here, B is here, and C is here.
Okay.
Yeah. Yes. So the triple ABC is say iterated pair. Yes. So AB, if A, B, and C each are in Sm, then AB is in Sm plus 2. And this Sm plus 2, it is C is Sm, but also in Sm plus 2 automatically. So this means that this triple is in Sm plus 4, and so union is a set of such triples. So union is a subset in Sm plus 5. Yes. Union is a subset in Sm plus 5, and therefore union is element is Sm plus 6. Yeah. So okay. So and in this case, C is the only element such that if given A and B, then C is the only element. So given A and B in Sm, C is the only element of Sm such that A, B, C, like this, in union, yeah, by definition. Now, if you open all brackets, it's this. So union is a relation between these three sets, or better to say, between this pair of sets and the third set C. Yeah? So this means that C equals union taken at the argument AB in our notation. Now let me put it in brackets. Yeah. So we have two things, two sorts of things. Union is some constant element. It's an element living at higher level, but anyway, it is an element of our universe. So union is, so let us put mu equals union, and u equals AB. Yes? And then we write that A union with B equals mu restricted on mu. So this means that we don't need separate operation of union. It is one of many operations which are reduced to two things, to some constant. Constant means this constant lives somewhere in the 6th floor, but anyway it is constant. It is some constant independent of anything. Yes, and the variables here are A and B. So for every given A and B, you can define their intersection, or if A and B are not of needed sort, yes, if they are, say, not in this level, but at higher level, for example, or if they are not sets at all, they are just individuals, then it gives 0. Yeah? And it is good because if union is not defined, then the result is no result or empty set. Yeah.
If I understand correctly, we never used like the nature of the union, right?
Yeah.
We only used the fact that it's some operator, so we could do that for any operator we can think of,
Yes.
right?
Yes. Yes, but we have to respect this order of levels. Yes, so we cannot say introduce an object which is a set containing elements from all levels. But if you are at some fixed level, then yes. So any such, you can introduce even very exotic operations with sets, yes, which are studied, say, in descriptive set theory, but they all live here in this universe. Yeah. Okay, so this way we define the terms, and then we define the formulas. So elementary formula is that say term mu equal mu, so it is formulas. And mu is element of nu. It is elementary formulas, and now you can combine these formulas. So if elementary formulas, now combine. So if you have alpha formula, then you can define not alpha. If you have two formulas, alpha, beta formulas, you can write alpha and beta. Yeah, alpha and beta. Now, if you have a formula alpha of x, it is a formula which contains x, variable x. Yes? Then you can write a formula. There exists x inside some term. Yes, term, its meaning is some set. Alpha of x. There exists x inside some scope such that this is true. That's it. And now again, you have a formula, you have these elementary formulas, and then you can combine them and grow longer and longer formulas. Yes. Now, formula is good in a sense that it can be right or false, true or false, yes? So this way automatically all formulas make either this or this sense. So we define the following things. It is semantics. Semantics is how to prescribe a sense to what we are writing, because what we are writing are just the sequences of symbols. So the meaning of, say, constant A equals A. If A is a name of A. Yeah? So A is just a symbol, and this clear A is element of our universe. The sense of, say, x is a variable, equals just x, nothing more. So x is a placeholder. When we substitute there something, it becomes a constant. So this way, yes, I would say that if you have a term containing or formula containing constants and variables, yes, then you can partially give a sense so that constants become elements of this definition of this formula, and our sense depends on x. So if you write simply x, then acquires some sense when you give x some value, some constant. Now, if you have elementary formulas, just a minute, you write meaning of set A and B. So we have two names of two constants, which are names of elements of S, is simply the pair meaning of A and meaning of B. Yeah, and what is meaning of A restricted on B equals, again, meaning of A restricted on meaning of B. Now, we write meaning, if you have the statement, say some alpha equal beta, where alpha and beta are terms, then you write meaning of this is true or false. The symbol for this is this symbol of alpha equals beta. This meaning is defined as I'm sorry, it's not. It is terms mu and nu. Meaning of mu equals nu is the same, and it is a meaning of the following statement. It is the value of mu equals the value of nu. Yes. So if this holds, there are two concrete sets or elements. Yeah. If this is true, then we say that this is true. Yeah. So this is, I would say, material. So we have two material objects, elements of our universe, and these are just two symbols. Yes, good.
If there are some free variables in our terms, in the interpretation, does it, like it wouldn't be true?
So remember, mu of x, yes, equal mu of x. Yeah, consider this term, so it is alpha of x equals alpha of x is this statement. Mu of x is mu of x. Okay, then for any particular x, this becomes this term without parameter, without variables. Yeah. So this means that this truth value also depends on x. Now we have to write the scope of x where it is changed. Yeah. It should be written somewhere, either in somewhere separately, or it can be part of this formula. In this case, alpha of x depends on x. Yeah. Now, consider this negation of alpha of x. Now I write here x. X can be a string of symbols, finite number of variables. Yeah. So let me write all this equals false if alpha of x is true if is false. Yeah. So this symbol again is read as truth value of a statement. Alpha of x is some statement. Yeah. No, for example, x squared equals -1. It is a statement. We can express it. The truth value of what are alpha of x and beta of x equals, no, it is given by the truth table of this conjunction. Yeah. If alpha of x is t and no, usually we omit this equals t. So if you write it, can be read as alpha of x is true. Yeah. So this itself is true or false, and false otherwise. What else? There exists x in some school mu alpha of x. So it is true when really there exists element x if there exists x in this set mu, it is I would say meaning of mu, this symbol mu is some set such that x is true. Let me write this. And then if you combine these elements, you can define more and more complicated formulas. Now in this formula, the formula which is written here, we have this x, but it is bound by this quantifier. This means that in fact x is not material here. Instead of x you can write y. Yes, again it is like this variable of integration. It is immaterial how you denote it. Yeah. That's it. Now I am going to define the non-standard model such that in some rigorously defined sense this has the same formal properties as our universe as check, but it contains, for example, infinite or infinitesimally small numbers. This was our goal. So let me do it. So to this, and so it is a construction of non-standard universe. You know what? Let me at this moment just start from the beginning. I will change a little bit notations. So I write as check. I denoted by U, universe. Yeah. So that we could use it freely. It is interchangeable now. Now suppose that I is some infinite set. I will choose later which set it is. No, for now you can imagine that it is a set of positive integer numbers, for example. But in fact, it's better to take it a little bigger. And f is improper ultrafilter. On I, so it is ultrafilter such that it does not contain finite sets. Yeah, so it's improper, and the basic properties of ultrafilter is that for any subset of I, this subset is element of ultrafilter or its complement is a subset. It is quite important for the future. And now we consider functions f of I in, say, S0 first. This function in S0. And I is element of our index set. Now I introduce the following relation. We write that f is equivalent to g if f of I equal g of I for almost all I. Almost all I means on the set which belongs to our filter. Yeah? Or almost everywhere. And it's easy to see that this is equivalence relation, so it is reflexive, symmetric, and transitive. Transitive because if you have, let me write, if A is subset of I, then you write mu of A equals 1 if A in F, 0 if A is not in F. Yeah? And this is has the properties of measure. This measure is finitely additive. In particular, if you have union of two sets of measure 0, then it has also measure 0. And the same for finite number. So we have this relation. And let me denote by W0 equal let me see, the set of f from I to S0, let me denote it by Z0, and we denote W0 equals Z0 factor for this of this relation. Yeah, so it is equivalence classes of these functions. And now I define further. I define Zn is the set of function from I to Sn, and Z union Zn. And now I wanted to define, have defined already W0, how to define the next sets. Here it is not so obvious, say how to define W1. W1, it is the set consider the functions f of I from I to S1. S1 is the set of sets. Yeah, no, it contains also elements, but also sets. I to S1, and now consider the function g of I to S0, let me put it dot I is here, I to S0 and g of I, elements of f of I almost everywhere. So this almost everywhere means not only that some g of I can be outside of f of I, but also that they can be, g of I can be the problem is that f of I is the values in S1, and S1 contains also all elements of S0. Yeah? So f of I for some I can be element, can be individual, so it has no element. So this makes no sense. And here we demand that this happens only on the set of measure 0. Now we say that G G equivalent H if G equals F equals H almost everywhere. Yeah? G and H are maps from I to Z. Yeah. And so, in particular, if G and H are the maps from I to S1, from I to S0, yes, then let me write I to Z0, S0. Then you write G and H. So if you consider equivalence classes of G such that it satisfies this, then the set of equivalence classes of G from I to S0 such that G of I element of f of I almost everywhere, yeah, so we take this, is denoted by MF. Yeah. So it looks again, so if this I, yes, and this, so for different I we have different sets because F is the value into this, the sets, yeah? So this is F of I1, this is F of I2, and so on. Then we consider, here it can be like this, we consider the function, all the functions such that they satisfy this condition almost everywhere. And also take into account that they can differ on a set of measure 0. So we have this set MF. And the set of all MF for all F into W0 is denoted by W1. So W1 is a set. So for any singular map f, the function f of I is some set for almost all I. Yes, we have a set of functions such that for almost every I, it chooses one element into set f of I, function g of I. Yeah. And now we continue it by induction. We define the set W1, and suppose that we have already defined the sets up to Wn. we define W0, Wn. Then how to define Wn plus 1 if f in z n plus 1, this we can define. So this means that f is a map from I to S n plus 1. Consider the set of G from I to Sn such that G of I, element of f of I, for almost all I. And now it is a map. Now in this set of such maps, you have a equivalence relation. So two such maps, G and H, are equivalent if they differ on set of measure 0. So this set occurred by the equivalence relation f equivalent H if f I equals H I almost everywhere is denoted by W. It's denoted by MF again. So MF is the set of all such trajectories through the set I, such that for almost all I we get into f of I. Yes? And the set of all MF for all f. The set of all MF, f in V n plus 1 is denoted by W n plus 1. Now, what is important here? Yes, no, okay, let us W check. It is union of Wn and from 0 to infinity. So, what is important here? That important here is the following, that W n plus 1 is always a subset of E of Wn. No, just look at the case n equal 0. So W0 is equivalence class of just functions from S0 to from I to S0. W1 is a set of such functions. Yes, it is a bundle of trajectories going through for almost all I through f of I. Yes, it is and it is so for almost just a minute. So W0 is the set of f of I from I to S0. W1 is the set of what? For any f, we have a set of such trajectories. Yes, and now f is also takes we take all possible f like this, so we have a set of subsets, set of sets of such trajectories. Yes, but nobody said that we can this way have all sets, all subsets. It is for any f is in W0, mf is a subset in W0. Okay? F1, W1. And F is a subset in W0. So again, it's important. So we take F in W0. So for any I, again, you have some set. So here we have this I, and for any I, you have some set in S0.
F would be in Z1, right? If I'm not wrong.
Excuse me?
F would be in Z1 for MF to be defined.
No, okay, F in, yes, no, I took F, already factorized it by this equivalence relation. Okay, let me take in Z1. Yeah? Now, MF is a subset of W0. Yes? And now if you take different F, you have different subsets. So if you take all F in Z1, you have some set of subsets. Yeah? So this means that all collection of MF, which is W1, is some set of subsets. Yeah? This means that it is subset of P of W0. So W1 is a subset of P W0. Yeah? No, similarly, Wn plus 1 is a subset in P of Wn. But it is not true that it is Pwn. It is smaller. It is smaller. The way we constructed it is quite restricted. Okay. And so let me denote. So I write S check equals U, W check equals union Wn, 0 to infinity, we denote by U star. Star is written to the left, no, it is historical. So in all books on non-standard analysis, star is written to the left. Okay. Now, among these elements, there are elements which we call standard elements. Of U star. So what are standard elements? Standard elements are elements generated by constant. Yes? So consider F in, say, W in, yes, Z0, F of I equals some A for almost all I. A in S0. Yes? Then consider the elements like this. And so MF is called a standard element of non-standard universe. Yeah? So if you have, say, the number 0, or let's say the number 1, yes, and consider the function such that for all I its value is 1, yes, then this is just 1, and we can identify our this 1, our usual 1 in as a real number, and these class equivalents of functions which are constant 1, class equivalence class of this function. Yeah. So, and so standard elements of W0 are identified with standard objects as 0. Yes.
What is called U star? Is it?
Excuse me?
U star is called a non-standard universe, or?
U star is non-standard universe.
Okay.
So its elements are, after all, derived from these functions f of I, but among these functions are especially simple functions which are constants. Yes, and for these functions, corresponding equivalence class and corresponding elements of non-standard universe are called standard. and they are somehow identified. And in this respect, we can write that S0 is a subset of non-standard universe. Now we can consider Wn and more than 0. What happens then? Then it is not so simple, because this element, if you consider, say, f of I from I to say Sn and more than 0. Yes, consider this map. Then corresponding MF is a set. Yeah? No, this is also a function with values in a set. But what we have instead here, the image of this f, is not a function with values in sets, but a set itself. No, after all, it is a set of such functions. Yeah? So we cannot honestly say that it is a standard element, and we introduce different notation. So in this case, one moment. So f I and S1, for example, Sn, and f of I equals some b almost everywhere, for example. So it is this is almost constant function. Then corresponding MF in Wn is a set. Of elements of Wn minus 1 Wz. Yes, because our construction is, I would say, inductive, or so at every point we have the tail of, at every step of this concern, we have the tail of previous steps. Is a set. So we write that MF equals B star. So B star is not B. It is maybe something very different. But B star somehow is associated with this B. I don't know how to call it. Call this operation. Making standard element non-standard, or I would say non-standard expansion of this element. Now let us consider example. In fact, it is the basic example in all this subject. Suppose B equals R. So consider the set of all real numbers. Why not? What is B star?
Is it B equal to a set of real numbers? Or
Excuse me?
B equals set of real numbers? B is equal to set of all real numbers?
Yes, it is a set.
Or
Yeah? B star. So we consider one moment. Consider a function f of I equals R. Yes? No, identically equals R for all I. Yeah? So what is MF? This MF is by definition B star. What is MF? MF is the equivalence class of functions. G I into S0. Now S0 contains as a part the set R. Yeah? Such that first G of I in R for almost all I. Yeah? So first of all, this. And equivalence class, no, there is no second. Equivalence class, by this relation, the two functions are equivalent if they coincide almost everywhere. So G equivalent to H if G I equals H I almost everywhere. Yeah? And so it is a set of equivalence class of functions. Let's see. So among these functions, there are functions which are constants almost everywhere, and then you have embedding of constants. But there can be functions which are not constants. So what are they? They are new elements. So if G of I equal, say, A for almost all I, then we identify G and G with A. Yeah? And otherwise, we have a non-standard number. Now, let's give a small example. Suppose this sequence, this function g of a, so I are integer numbers, and g of I is the following. So it is 0 when the I is even, and 1 if it is odd. Yeah, 0, 1, 0, 1, and so on. What can be said about these functions? No, we have two sets, where one set where g is 0 and other set where g is 1. Yes, they together give the whole I. But we have a property of ultrafilter, that if I is a union of two sets, with joint sets, that one of them has measure 0 and one has measure 1. Yeah? So in this case, if even sets have measure 1, then this number is this is in fact 0, because these ones are negligible. The function is 1 on negligible set. Yeah? Otherwise, this function is 1. And what happens depends on ultrafilter. We cannot say it a priori. It can be this or that. Yeah, so we'll see further other uses of this property of ultrafilter. Okay, unfortunately we have to finish today. So next time we will go on.